In this video, we're going to discuss free energy. So let's start our discussion of free energy by reviewing the second law of thermodynamics. The second law of thermodynamics defines what a spontaneous process is, and it tells us that the total entropy of a system plus the entropy change of its surroundings will always increase when we have a spontaneous process. And we said we could restate the second law mathematically, as you can see here. Now, remember, if you review the video on the second law of thermodynamics, we can express the change in entropy of surroundings in terms of the enthalpy of a system, the negative enthalpy of the system, divided by the temperature. So let's take this equation and let's manipulate it just a little bit. Let's multiply this equation through by temperature. If we multiply everything by temperature, we get an equation that looks like this. Okay? Now let's do one other thing to it. Let's just multiply through by a -1. Okay? If we multiply this whole equation by -1, then we get an equation that looks like this. So we're just taking the second law of thermodynamics, the mathematical equation for it, and we're manipulating it slightly. Now we have our equation that looks like this. This term right here, the negative temperature times the change in entropy of the universe, we're going to call it delta G, or the change in free energy. And that's also called the Gibbs free energy. So now we're just going to rearrange this a little bit. We said that this term right here is equal to delta G, and then we're going to write delta H of the system first, minus T times delta S of the system. So here we're not going to put these anymore, but it is important to appreciate that delta G is equal to the change in enthalpy of the system times the temperature times the change in entropy of the system. So we've expressed everything here in terms of the system. Even though we generally don't write those, you do want to keep that in mind. Okay. So Gibbs free energy. As we said before, since the change in entropy of the universe is obtained from the delta S of the system and delta H of the system, everything here is written in terms of the system. Now that's important because we can readily measure changes in entropy and enthalpy of the system. Systems are much easier to measure than surroundings. So it's much easier to measure. That's why we like to write the second law of thermodynamics in terms of free energy. It's also a state function. Delta G, free energy change, is a state function. It only depends on the initial and the final state, not the path to get from initial to final. So we said that delta H of the system, we like to express things in terms of the system because we can calculate it. So we can calculate delta H of the system using a variety of different techniques, everything from Hess's law, enthalpies of formation, etc., etc. So we can readily calculate this value if we needed it. The entropy change of our system, this guy, we can readily calculate it using a formula that we've seen before. The change in entropy of the system, generally under standard conditions, is equal to the sum of the entropies of products minus those of the reactants. So we can readily calculate the entropy change of the system. And the temperature, we can very readily measure that, but it must be on the Kelvin scale. Now, Gibbs free energy, a bit more about that. Gibbs free energy, or G, is the amount of energy available to do work. So when reactions occur, they release energy, and some of that energy is available to do work. So chemical reactions or physical processes can either release or absorb free energy. If you have a reaction that releases free energy, delta G is negative. So a negative delta G value means that energy is released from the system into the surroundings. That's what the negative sign indicates. And we call that an exergonic reaction, not exothermic, but exergonic. If you have a chemical reaction or physical process that absorbs free energy, so here we have energy being transferred from the surroundings into the system, well, that gives it a delta G of a positive sign. So a free energy change with a positive sign indicates that we have free energy being absorbed by the system. And we call that endergonic. So be familiar with these terms. And why is it important to study free energy or be able to calculate it? Well, the energy released from a chemical reaction can be used to do work. That's what we mentioned, and that's a big thing of chemistry. We want to use chemical reactions to do work. An example of that would be the combustion engine in a gasoline-powered car. We're using the energy released from the combustion of octane. So we have octane and gas and oxygen, and we react those to form carbon dioxide and water. And this process has a very exergonic process. It releases free energy. We can use that free energy to do work, move pistons up and down, and power our car. So that is very beneficial to us. Another reaction are the batteries in our cell phones or computers. We have lithium-powered batteries a lot of times, and those undergo chemical reactions that release free energy. So we can calculate how much energy is released that we can do work with, power our cell phones, computers, etc. And also biochemically, here we have the hydrolysis of ATP, breaking ATP into ADP and phosphate. This is, again, an exergonic process. So your body takes advantage of chemical reactions that release energy and uses those to do work, power muscles, heal wounds, etc. So calculating and understanding free energy is very important in everything from engineering to biochemistry and pharmacy. So because our Gibbs free energy equation is derived from the second law of thermodynamics, the Gibbs free energy also allows us to determine whether a reaction is spontaneous or non-spontaneous under certain conditions. A delta G that is less than 0, or negative delta G, that process will be spontaneous under those conditions. A reaction that has a positive delta G will be non-spontaneous under those conditions. And if you have a delta G equal to 0, then that reaction is at equilibrium. So much like the second law of thermodynamics, our delta G equation, our Gibbs free energy, allows us to predict whether a reaction is spontaneous or non-spontaneous under a given set of conditions. Now, a lot of times when we carry out reactions, we carry them out under thermodynamic standard state conditions. So just like other reactions, if we carry out a reaction at a pressure of 1 atmosphere, at generally 298 or 25 degrees Celsius, 298 Kelvin, 1 molar concentrations, we call those thermodynamic standard conditions. And then we can write our delta G equation the same, but we just put the little standard state up here to indicate that all our conditions were under these standard state conditions. So be familiar with what these indicate or what these mean when we say thermodynamic standard state conditions. Let's take a look at a problem. Take a look at this reaction and the information given and see if you can calculate the free energy change for this reaction under these conditions. Pause the video and give it a try. So here we want to calculate the free energy change, and we're given standard conditions, and we're given our delta H standard, our delta S standard. So we want to use this equation right here. So we're solving for delta G standard. We plug in our enthalpy, which is negative, this is exothermic, minus the temperature, must be in Kelvin, be sure you change that to Kelvin, times our entropy change. Again, here we have a negative entropy change. So we want to solve this, but one thing we want to pay attention to are the units. Here we have our delta H value is in kilojoules, and our delta S is in joules. So we have to change one of those into either kilojoules or joules. Here I've decided to change them both into kilojoules. So I've changed my entropy value into kilojoules. Then we can solve, and we should get a delta G value of negative 33.0 kilojoules, which indicates that this reaction under standard conditions is exergonic and therefore spontaneous. So be sure you're familiar with what free energy is and how to calculate it in terms of enthalpy and entropy.